Okay. So welcome everyone. Today I'm talking about the recent developments for DFT-based MS modeling. And the idea here is to make this program very, very simple. And the reason is that the majority of data sets in metabolomics are now generated by LC-MS. And so lots of labs work with tandem mass spectra, they work with liquid chromatography, and they want to really gain insights. So here, a tool that really can explain fragmentations or create CID MS spectra could be very valuable. The simplicity starts with that you can put in the molecule as a name. You don't need to create structures, you don't need to know about 3D conformers, you just give it a name. The molecule is pulled from PubChem, already 3D optimized. You can create protomers and deprotomers for positive negative ionization mode. We perform very fast ab initio density functional theory calculations. In this case, we do that on GPUs, not CPUs, on graphical processing units. Similar, the same ones you can use for gaming at home. We calculate charges in fragments. We perform a statistical analysis of all the fragments and then compile a CID MS spectrum that you, for example, could upload to MONA database, to GNPS, to the NIST spectral library. And we also have trajectories. And I have shown, or we have seen many of those also from our students, Young and JC. And the idea here is basically that if I can start the simulation, that we can see the collision with our collision gas and bonds break and form. And that is very, very important. It's not, we cannot use a simple molecular dynamics simulation. We really have to use ab initio molecular dynamics, because only ab initio molecular dynamics can form bonds and break bonds. The simulation takes around 220 seconds on a DFT level. We see there the omega P9070X with the PCSec1 Jensen data basis set. This is very, very fast. Usually DFT optimizations alone would take several minutes for medium and larger sized molecules. And the reason why we are so fast is really to run that this code is running on graphical processing units, which have thousands of streaming processors. So here we work with, I think, 10,000 streaming processors, which is like 2 or 3 GPUs only. So it's a normal desktop machine that you can put under your desk. And here we see a loop of what actually happens during the simulation and why these are so valuable. So we see, and I have to start it again, we can see a water loss on the bottom. You can see the water drifting away and then carbon monoxide. But at the same time, the molecule splits, but forms again with other parts. And these kind of rearrangements are very, very important. And yes, this is a small molecule. We can extend it also for larger ones, but that's the whole idea. We can have a look inside the mass spectrometer, and that is something really, really amazing. And we can use this knowledge, the fragmentation knowledge, not only for teaching purposes, but really for research. We see very clear our reactions here. We see water loss, CO loss, we have seen that, I showed you that, C2H4 loss, fragments that are very easy to explain. Now consider a molecule that you have never seen before, a complex natural product. And it's very hard for experienced mass spectrometrists to even explain those reactions. They can do that on paper, but having a ab initio model with a very accurate method, DFT, can give you really all the information. We can also do larger molecules like caffeine and scopolamine. And of course, we investigated over 30 different DFT functionals and also a number of base sets to see how good they are. And usually long range and double hybrids are very well in this kind of simulations. Simplicity, user friendliness, and speed can hopefully bring wider community adoption. That goes for teaching purposes, research purposes, and if we cannot wait, for example, 3 hours, like for those small molecules, we can also do it on the cloud. And if we can do that there, such a computation could be over in 220 seconds. So with that, thank you very much.